In this portion of the unit, we're going to talk about acids and bases. We're going to talk about the definitions of an acid and a definition of a base, and we're also going to talk about how to predict the products of an acid-base reaction. Now, there are going to be two types of acids we will discuss. The first acid we are going to talk about are Arrhenius acids and bases. And with an Arrhenius acid, they produce hydronium ions in the solution. And an Arrhenius base is defined by a substance that produces hydroxide ions in the solution. So if we take this example where you have hydrochloric acid and sodium hydroxide, the reason why we know hydrochloric acid is our Arrhenius acid is because if we look at the elements or ions it breaks down, this molecule, HCl, it ionizes to form H plus and Cl minus. Now, sodium hydroxide, the reason why we know sodium hydroxide is our base is because if we look at this, when sodium hydroxide dissolves in water, it dissociates to produce sodium ion and hydroxide ion. So by definition, sodium hydroxide is our Arrhenius base and hydrochloric acid is our Arrhenius acid. Now, the second type of acid-base we're going to talk about are Bronsted-Lowry acids and bases. Now, with the definition of a Bronsted-Lowry acid, it is the proton donor. So, for example, sulfuric acid is a proton donor because it's going to lose a hydrogen ion or hydronium. Now, a Bronsted-Lowry base is going to be something that accepts this hydronium ion. So SO4 minus 2 is going to accept the hydronium ion. So for example, if we take this example, where we're having water and ammonia, which is going to be the donor and which is going to be the the base. So if we look at this, we can make a prediction of what our products are going to be, and that is OH minus and NH4 plus. So what's happening is this hydrogen on the water is being donated to the ammonia. So that tells me that water is our acid because this donated a hydrogen, and this is our base. Ammonia is our base because it accepted the hydrogen ion. Now those are the two different types. So one deals with proton donating, while the other one deals with which one has the hydronium ion and the hydroxide ion in the solution. So you should know the two types of models, the Bronsted-Lowry and the Arrhenius model for acids and base. Both are correct. We just have different ways of defining them. So let's go ahead and define which ones are our strong acids. So acids and base strength. How do we determine this? Well, strong acids and bases completely dissociate in water and are strong electrolytes. That means that when I put hydrochloric acid, the hydrogen and the chlorine completely dissociates. And weak acids and weak bases somewhat dissociate in water. They don't like to separate from each other very well, and they're considered weak electrolytes. So just a quick reminder, dissociation means it breaking apart into ions in the solution. So when you add sodium chloride into water, it dissociates into its ions, sodium ion and chlorine ion. So Now, here are some examples of strong acids and strong bases. This slide shows you all the strong acids. If they're not nitric acid, hydrochloric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid, they are all considered to be weak if they are not these six. If you have strong bases, they're considered lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. If you notice, these are hydroxides with the alkali and alkaline earth metals. If you notice in the name of the elements, their groups are already indicating that they're going to be forming basic products because of alkali and alkaline earth. So if they're not one of these types of hydroxides, then they are all considered weak bases. So if you have a copper hydroxide, that's considered a weak base. Now, if we talk about acids, there are also what are known as monoprotic, polyprotic, and amphoteric. With monoprotic, that means it only has one hydrogen to donate. So if you notice, an example is nitric acid. Here, nitric acid has only one hydrogen to donate. Another example would be HCl, because it only has one hydrogen to donate. And another one would be HI, because again, it has only one hydrogen to donate. Now, if we take a look at polyprotic acids are considered to have more than one hydrogen to donate. So if you look at sulfuric acid has two hydrogens to donate. So we're going to call this a diprotic because it donates two. Phosphoric acid has three hydrogens. This is called triprotic because it has three hydrogens to donate. Now, this polyprotic acids some of sulfuric acid is strong, some of them are not. We are going to learn about how these reactions and what type of products are formed when they go through neutralization. And so the last thing we're going to talk about before we move on and talk about how neutralization reactions are amphoteric. Now, amphoteric means that you have a compound which both accepts and donates protons. Now, they are very special because they act as an acid and they also act as a base. So water is one of our biggest amphoteric compounds there are. It acts as a base and it also acts as an acid. And we will see some of these in our problems in the future. So let's go ahead and define neutralization reactions. Neutralization reaction is when you have an acid and a base that combine and they form water and salt. So you're always going to have water and salt for most part. Now, you can also write net ionic equations for these, and you always have to consider the strong and weak acids, but we will definitely talk about mostly strong acid and strong base in the following examples. Now, just want to remind you, a salt is an ionic compound formed in a neutralization reaction, and it has both an anion from an acid and the cation from the base. So remember, it's like a double replacement. So let's go ahead and do a few examples. In the following examples, we're going to predict the products of the neutralization reaction, and then we're going to also label which is the acid and which is the base. So for this example, we are doing the neutralization of sodium hydroxide and hydrochloric acid. Since this is a neutralization reaction, we can think of this as a double replacement. So the sodium and the hydrogen are going to swap places, giving us a product of water, and a salt. Now, let's go ahead and notice that when you do a double replacement or for the neutralization reaction, you end up with water and a salt. Sodium chloride in this example. Now let's go ahead and label which one was our acid and which is our base. So for our acid, if we think of our Arrhenius model, we can definitely just label which is which. I could tell you right now that HCl is our acid and NaOH is our base, because according to the Arrhenius model, in order for us to have a base, you have to have the hydroxide, and if you have an acid, you have to have the hydronium ion. And again, this dissociates to H plus and Cl minus. This dissociates to Na plus and OH minus. That's just by the definition of Arrhenius acids and bases. Now, if we look at Bronsted-Lowry acids and base, you can definitely tell which is the hydrogen donor, and that is HCl, and the hydrogen acceptor is sodium hydroxide. And by the Bronsted-Lowry definition, HCl is our acid, and NaOH is our base. So I want you to try example 2 and example 3 on your own. And when you're ready, I want you to go ahead and press play again to check if your answers are correct. So go ahead and press pause. And now here are the answers. In this problem, we're predicting the product for potassium hydroxide reacting with acetic acid. And since this is just a double replacement, we're going to swap places with the potassium and hydrogen, and you end up with H2O for water and potassium acetate. Now, to label acid versus base, we really can't, we can really use the, either of the models, so Arrhenius or Bronsted-Lowry, and your acid should be the acetic acid, which is HC2H3O2, and your base is potassium hydroxide. Now, with this example, I want you to notice that there's sulfuric acid, which is a diprotic, because it has 2 hydrogens to donate, and we have aluminum hydroxide, which is not on our list of strong bases. So this is going to be relatively a weak base. And if you really want to do this properly, when you have a diprotic plus a base, you're not going to have a complete neutralization, meaning that our products here, you're just going to remove one of the hydrogens, not both, only one of the hydrogens, so you should end up with an ionized form of sulfuric acid, and it has a minus, and you end up with aluminum hydroxide, and 2, and the whole entire thing is pretty much a positive, and you have water. Now, you can continue this process of removing the hydrogen, and you end up with H2O plus SO4, 2 minus, plus eventually you'll have aluminum 3 plus, aluminum 3 plus. So eventually it'll all react, and if we balance this correctly, you should have the salt be formed, and the salt you form is H2O plus aluminum 2 sulfate. Now, since this is not a strong base, these process probably won't be easy, so it won't necessarily occur, but we can definitely have this first process go through, and we can talk about this in class. But hopefully you get the concept of this. Thank you. And look for the next set of tutorials.